Okay, thanks. So I asked Bill to go ahead because he introduced a lot of things on my initial slide, so I don't have to repeat. Okay. So broadly, as I said, like we have been working in the MVAPICH2 stack for some time, and most importantly in the recent years, like we are a partner of the NSF TAC Stampede system. So if those of you who don't know, this is an IBFDR with Intel mic up to 6,000 nodes. So this is where like all our work we are doing, and I'll be trying to share our experience on this system. So for last 2 years, as many of you know, like we already have supported accelerators from NVIDIA GPUs, both like Fermi and Kepler and all. So as the Intel mic came and as a part of the Stampede project, so we got involved in this. So there are some designs ongoing, and this is a different design. We are not using the UDAFL interface, what Woody mentioned and Bill mentioned. So we are working on the standard OFET stack with the VERS interface, and that is our approach, which is a little bit different than the Intel MPI's approach. Bill indicated very quick, indicated about these programming models. I'll quickly go over it, and then you will see that to put together the complete MPI stack, there are all these different paths. You need to worry about intra-mic. That means how the mic process within a mic talk to each other, intra-node. So that means within a node, how the mic process and host process talk to each other. And finally, inter-node, that means the mic-to-mic talk across the nodes. And I'll show some early performance evaluation numbers as I indicated earlier. So this Bill has already introduced, so I'll skip. So this is one, I'm taking the slides from Scott from Intel. So the broad idea is, some of you might have seen that. So this is like a variety of programming models which are being planned or being proposed by Intel. So the first one is, of course, multi-core hosted. So that means only the multi-core GN is running the program. The offload mode, where you are mainly running on your multi-core, and the GN is trying to do the offload. So that is also the current models most of the systems are using. These are the two newer models which bring the challenges for designing a very good MPI stack. So one is the symmetric. That means the same program you're trying to balance out between the multi-core GN and the mic. And finally, this is the many core, so that your application is purely running on mic, nothing on the host. The host is just like being used as a bypass. So this is our focus here, like how we can really support this kind of symmetric mode, and that with a good performance and scalability. And that's what we're trying to work here. So here to go into a little bit details, I think Bill indicated that in one slide. I'll just go into a little bit more details. So this is like the offload mode. So that means you are basically, every node is trying to offload things to the mic, but the communication is happening between the processors. So that's the normal thing. So here, like there are all these different, Intel mic has this offload capabilities. So MPI communication is intra-node and inter-node. So these are the two modes you need to provide. And this already, like we have the MVAPICH2 stack, where we have the shared memory within the node, and also the InfiniBand. And this is the model which is currently running at the Stampede. So if you go into the Stampede, try to use the MVAPICH and run, this offload mode is being used there. But now this brings the additional challenge, like in the symmetric mode, if we just want to like copy here, the data movement between the mics. So one is the intra-mic. So that means within a mic, let's say there are 61 cores. So how these cores talk to each other. So that is the first thing you have to provide, so that you can really run an MPI process on one of these cores. And then, of course, the inter-mic. So that means if this mic wants to talk to this other mic, so how do you do the host bypass? So that is one of the challenge in this mode. And this is the most complex mode. So that means all these paths, I think Bill also indicated, these are all these MPI paths. So in the MPI stack, you have to worry about like intra-node, inter-node, intra-mic. So that means within the mic, inter-mic, host to mic, mic to host. So there are so many possible MPI paths, and this makes it really complex and challenging. And the more we see it, optimization is a nightmare, okay? Because there are so many paths, and every platform now you need to think of, like it can go with IBQDR, IBFDR, it could be Sandy Bridge on some particular speed. Tomorrow it will be Ivy Bridge. So all characteristics differ. And then how do you not only design all these paths, but you need to optimize, because if you don't optimize, then you don't get the best performance from the collective layers or from the top layer. So there's a huge amount of work involved to really bring out an MPI stack. So I just want to give that kind of a warning to start with. So what we have done here, like 3 kinds of designs I'll show, and then try to put it together and then show some of the performance numbers. So the first one is the intra-mic. So that means within the mic, how we allow the MPI process to talk to each other. Okay? So here what happens is like in our MPI stack or any of the other MPI stacks, there is a shared memory channel that within the host also, let's say we have the Sandy Breeze or Westmere or any of these multiple cores, they talk to each other using shared memory because shared memory is much more faster. So that is there. So then we also used the skiff, which was introduced earlier by Udi and Bill. So we used the CS3, that is the CS3 is the channel 3 layer of our MVAPICH2, and then we extended that. So it is a low-level communication interface over the PCI bus, can be used for intra-mic, and allows more explicit use of the DMA engines on the mic. And that actually allows MPI process to be efficiently run on mic. With this support only, you can run things within the mic. They cannot talk to outside, but they can run within the mic itself. And then we had to actually take not only processes within the mic talking, but let's say I have 16 cores on the Sandy Breeze and 61 cores on the mic. How do they talk to each other? Let's say I run an MPI job of 76. Sorry, my maths. 61 plus 16, 77. So if I run a 77 MPI job, how do they talk? So in order to do that, we need to provide some additional channels. So here we had to provide, like, this is the basic IB, which is there. So we had the IB skiff, which is this red line. And then this is the standard skiff. So by providing these kind of channels, so these allowed actually our MPI process to efficiently run on a mic and node and a host, just on a single node. So you can run any type of combination, and I'll show you some numbers later on with this. And then finally, now the question comes is how do we do inter-node? Okay, so now let's say mic on this node is trying to talk with the mic on the other node, and now we have to go through the PCI, like the peer-to-peer, like from one mic to the InfiniBand, then going over the InfiniBand fabric, and then going to the other. And here we have some issues, and this issue I think was indicated earlier. So especially this comes with Sandy Breeze and Intel mic. Okay, so if you think of like this is your host Sandy Breeze, and this is like the mics, and then this is the IB. If you carry out these different kinds of data transfer, like mic to remote on the host to mic, which is intra-IOH, depending on where your mic is there. And here you'll see that the performance varies a lot. So here you see this is the green line is the best. You get around like 5,000 megabytes per second, but this is 900, this is 370, this is 1,079. So this is the performance degradation, which a lot of people have been talking about. So what it means that the performance of IB reads from mic is limited. Okay? So that means communication performance between even the mic to the remote host is also limited. Okay? So with that kind of things, you need to really avoid this, otherwise you will not be able to design a very balanced MPI stack. And this is where what we try to do, it is this reading from this mic is different, but if you see from the mic to the host, this is good. I mean, you get here around 6,900 megabytes per second. Similarly, writing also is good. So what we had to do here is to introduce this proxy design. I think Udi mentioned this earlier also. So if you put a proxy, instead of trying to do a peer-to-peer transaction, we are taking it to the host, and then from host we can send it to the others. Okay, and that is the design we had to put. And in order to do that, we have to actually now add some more things. So let's say this is a node 0 and this is a node 1. So this is the GN5, this is the host proxy. On the other hand, this is the host proxy, and that's the GN5. So now we need to introduce this. This is the host proxy here, and then another host proxy here. So now you can see there are different lines. So one is the red line, which is the direct InfiniBand. You can talk, which the basic, like the OFET stack, which Intel provides. And now for the other one, you have to take it from the GN5 to the host proxy. Then from host proxy, you send it to the other host proxy on the remote node. And from there, you take it to the mic. Okay, so it will go through like multiple hops to really alleviate this performance bottleneck, what we had seen earlier from the peer-to-peer transaction. Now there is, of course, here there is like the direct IB, you can get low latency, and then this is the IB skiff is the high bandwidth, and obviously within the MPI stack, we can actually make a choice. I think Bill also mentioned this, so that you can actually choose the best way to do the transfer with the where to use the low latency and where to use the highest bandwidth. So this is the kind of designs what we have put it together. So now let me show you some performance evaluations and see how these designs are coming up. So first is the point-to-point. So this we are trying to show intra-node both on the host intranode both on the mic also. So what it means that this is like the intra-host. So that means on the Sandy Bridge, two cores are talking, and that is always the first. I mean, here we get around 190 nanoseconds for very short messages in the MVAPICH2. We can talk core to core. But in the mic, within the mic, as I think Woody mentioned, these mics are slower processors, and each and everything, whatever you do, matters. Okay? And we have been spoiled by doing this design on the Xeon, and now it is hurting us back. So here you will see that mic to mic, we are getting around like a 3 microsecond. This is for short messages, and these are the numbers for host to mic and host to mic and mic to host on the same node itself. Okay, and the right-hand side is trying to show the similar kind of things for large messages, and here again you see that the host numbers are always good. That means the within the node they are very good, and then the host mic to host fall in between, and this is the mic to mic. That's the intra mic is slow. And this is the design we have done based on the MVAPICH2 1.9b, which was released like few months back, and we are just updating it to the 1.9 RC1, which was released 2 weeks back. And then these are all these numbers are on the TAC Stampede system. So that is the platform which we are using, and whatever the latest MPSS stack is available there, and this is with IBFDR. And then that is the latency, and these are the bandwidth. So here again, you can see the similar kind of trend. So this is the bandwidth for unidirectional bandwidth, like we are trying to pump from one side to the other, and this bidirectional bandwidth where both are communicating. And here we see like on the host, we can get very good bandwidth. Intra-node on the host, we have those of you who are familiar, like we have a module called Limit, which is like a kernel 0 copy, so we get very good performance with that. But that we cannot run currently on the mic, so we need to talk and see whether people are trying to provide some additional support so that this kind of kernel modules can run. Currently, there is no way to run those kind of stuff. And with that, actually, I think within the mic also we can push the performance up. Yes. Okay. So that's why you see the performance is low here. Otherwise, that can actually go up. And then the mic to host and host to mic are here. And then the bidirectional bandwidth is almost the similar kind of a trend we see here. Now then going to the internode. So that means one mic here talking with another mic here. This is really going over the network, and then this is the proxy design. And this is where we see the difference. So the latency-wise, we don't see much difference. The IB is good enough for short messages. But now if you see the large messages, this is the big difference we see. Like even in the large message latency, so the default one is very high, okay? Because of that, like a read and all I was referring earlier, because the performance is not good, that is getting reflected. Whereas if you do the proxy-based design, you can reduce the latency significantly. And that becomes more prominent in the bandwidth numbers. So this is the internode mic-to-mic MPI bandwidth. So that means we are really pushing data from mic from here to the mic to the other node. And again, small messages, we don't see the difference, but large messages, you see almost by a factor of 5. Okay? So if you just don't use this kind of a proxy design and depend on whatever we do on the Sandy Bridge, currently the peer-to-peer, you will be limited with only 1,000 megabytes per second. And here you can push up to like a 5,100 megabytes per second. So that is the new proxy design is bringing us. And that is coming very close to like the FDR. It's not the FDR limit, but because of the overhead of the proxies, because we are going through so many hops, we are losing some performance there. And then this is the bidirectional bandwidth, a similar kind of trend we see. Short messages, we don't see much difference, but the large messages we again see, like instead of 2,000, here we are able to go up to like 8,000 plus megabytes per second. Okay? So with this design, actually, when you put it together, now everything runs. You can actually support symmetric mode, and that too with a good performance. And that's what we tried to show something here. So these are very recent experiments we did. So here it is like, think of like an all-to-all. We are running on 128 processes on 16 nodes, but pure mic. So that means we are not even involving the host processes. So we have 16 nodes. On each of the mic, we are taking 88 processes, and they are talking. Okay? So that is 128 all-to-all they are trying to do. So this is one of that symmetric mode, which is the extreme right. So that means we are using the pure mics only here, not the host processes. And now you can see the new optimized design, like whatever with the proxy-based design, is really helping us to push the all-to-all latency lower. And so here we try to really do the symmetric, okay, like both host and mic. So the configuration here is the same 128 processes, but now we are running on 8 nodes, and on each node we are taking 8 host cores and then 8 mic cores. Okay, so now all kinds of communications are happening. All those lists I showed, like within the mic to host, host to mic, across. So all communications are happening together. So we are trying to bring all our optimizations just to see what is the overall effect here. And we see very good performance here. So that's the default versus this optimized design. And then we try to run some basic benchmarks. So these are after some initial collectivity evaluation, we went upper layer. So this is a standard 3D stencil benchmark. A lot of applications are based on that. You basically get exchange data on the X, Y, Z dimension kind of things. And see similar kind of things we did, like 128 processes, pure mic, and there also we see much more improvement. So with this kind of design, so these are the initial numbers we have with the complete design. Of course, we are still doing extensive testing. And the more important thing, as I said, this tuning. Okay? And this tuning has a lot of approach. I mean, complexity in the sense, not only just point-to-point paths, but now you need to rethink of all collectives. This is a big issue, because the host processors are so fast and mic processors are slow. Now think of a broadcast, think of an all-to-all, reduce, all those collectives, those old algorithms, they will run, but that is not the best way to do it. So it is a new research direction one has to actually solve. I don't think it will take some 2-3 years to resolve all these algorithms for heterogeneous mode. Then only you will get the best performance out. And so we are trying to look at some of the new algorithms and then trying to make sure that we also validate with all the different kinds of applications, because there are so many paths. We need to make sure that all the paths are working together in the most correct manner. So we'll be taking another 1 or 2 months to fix all these things and plan to release it. So that is on our roadmap. So with this, I'll close here. If there are any quick questions, I'll be happy to answer.